Our solar system is a wondrous place with a single star, our sun, and everything that orbits around it: planets, moons, asteroids, and comets. What do we know about this beautiful solar system we call home? It's part of an even larger cosmos with billions of other solar systems.
Hi, I'm Jim Green, Director of Planetary Science at NASA, and this is Gravity Assist. With me today is Dr. Amy Simon. She's a planetary scientist from NASA's Goddard Space Flight Center. And we're talking about the ice giants. These are two enormous planets in our outer solar system. They're Uranus and Neptune. Now, Uranus and Neptune are probably the least known of all our planets. And the reason, of course, is only one spacecraft had visited them, and that's Voyager 2. Flew by Uranus in '86 and Neptune in '89. So, Amy, what do we mean by ice giants, and what are these objects all about?
So Uranus and Neptune are really unique in our solar system. They're very different planets than the other ones we think of. And part of the reason we call them ice giants is because they actually have a lot of water ice. So while some of the other gas giant planets are mostly hydrogen and helium, they're predominantly water and other ices.
You know, that's kind of amazing when we think about that. How were they able to acquire that?
So these planets form much farther out in the solar system where there was a lot of ices available. And they didn't quite form as big as, say, Jupiter or Saturn, so they couldn't pull in quite as much gas. And so that's kind of part of why we believe they're so different.
You know, some of the simulations on how our planets formed seem to indicate that they formed closer to the sun, and then through gravitational interactions were pushed out. And that includes Uranus and Neptune. Could they have acquired a lot of the Kuiper Belt objects as they were doing that?
Absolutely. As a matter of fact, we think that a lot of Neptune's moons are captured Kuiper Belt objects.
Yeah, that's kind of gives it away a little bit, I think. And of course, that one moon that we love so much at Neptune, called Triton, that's such an unusual body and was quite a shock when Voyager 2 went by. Why is that such a different moon?
So Triton really is just such a bizarre world. For one thing, we think it has geysers on it, but these aren't geysers like we're used to on Earth, where we have hot water and steam. It's so cold that we actually have nitrogen ice spewing out of the surface. And so that's really weird to start with. But if you move away from the south pole of Triton, then you get into this weird terrain that we call cantaloupe terrain, because it looks like the skin of a cantaloupe. It's all wrinkly, and we have no idea what's forming that. And we've never even seen the other side of Triton. So who knows what's on the other side?
You know, are there any analogies between that cantaloupe terrain and some of the terrain we see on Pluto?
There is some, and a lot of this has to do with the fact that they're so cold, and even though they're cold, they still have some sort of activity that's moving the ice around. And so we think that Triton and Pluto actually have quite a lot in common, and that's something we'd like to go back and learn a lot more about.
You know, Triton's such a spectacular moon. It's larger than the body Pluto, and as we talked about, may actually be a Kuiper Belt object. But it also has a funny orbit around Neptune.
Right, so all the planets in our solar system move in the same direction. They all pretty much rotate in the same direction. All their moons go around them in the same direction. But Triton doesn't. It's retrograde, so it's going backwards. And this is partly because we think it was captured, so it got too close to Neptune and got stuck there.
How hard is it to see Uranus and Neptune from the Earth?
So Uranus and Neptune are so far away, they're just really faint. And so the ancient astronomers that originally found the other planets didn't even see Uranus and Neptune. It took telescopes to find them in the first place. So if you were to go out and look, you'd have to know exactly where to look, and you'd still need a telescope to be able to find it.
Since it required telescopes to see Uranus and Neptune, when were they discovered?
So Uranus was first seen by Herschel in 1781. Neptune wasn't seen for almost 50 years later, in 1846.
You know, the discovery of Neptune is really kind of fascinating in the sense that observing Uranus really gave away the fact that there's something else out there. How did that go?
Yeah, you know, that's kind of interesting. That's actually how they inferred all these outer planets, was they were looking at the orbits of planets closer in and kept seeing them being tweaked a little bit, and they kept inferring there had to be something else out there, or something with a lot of mass pulling them around. And so that's kind of how we got an idea there was a Uranus and a Neptune. But even after that, we still thought there was more mass out there, which led to the hunt for Pluto.
You know, I think it took a long time to really find Pluto because of Uranus's perturbations. It had to go around the sun at least once during that time period to be able to understand its full perturbations. But it was that really discovered Neptune.
Correct. So it was almost 80 years to the date when they found Pluto, and it's partly because they knew where to look. So you're looking at regions of the sky with photographic plates and trying to find something moving in the right place in the sky to be able to find it.
Uranus is one of those planets that I think is so featureless. Why does it look like that?
I think poor Uranus is misunderstood, actually. Uranus is very bland in appearance most of the time. It's kind of a pale blue planet. It's the real pale blue dot. And part of it is just that it is so cold. And it doesn't have a lot of internal heat. All of our outer planets, our giant planets, give off more heat than they receive from the sun, except for Uranus. And we think that is slowing down convection inside the planet. You don't get the equivalent of thunderstorms, so you don't see the bright clouds on Uranus that you see on the other planets.
Another really fascinating aspect about Uranus is its rotational axis. It's so different than all the others. Why is that?
Yeah, that's another big puzzle. So Uranus is tilted over on its side. So if you were looking straight up in the solar system, that would be 0 degrees. It's tilted over 98 degrees. So it is pretty much rolling around on its side. And we have no way of making it do that. And so the best guess we have at the moment is that while it was forming, it collided with something even bigger or as big, and it got knocked over. And so that's a real puzzle when we try to explain how the solar system formed.
Are all the Uranus moons in the same plane in the equatorial region?
They are, and so it's a little different than what we can see on the other planets because it is tilted on its side. We get a different view than we do when we fly by other planets.
You know, in addition to the fabulous moons that Uranus has, doesn't it have rings?
That's correct, actually. All of our outer planets have rings around them, and Uranus's are very narrow. It has about 9 rings. They're hard to see because they are so narrow. We were able to see them with Voyager 2, and that's how we discovered them. But rings are great because they're one way that we actually can do kind of the equivalent of seismology on the planets. We can look at how the rings oscillate and how their shapes change and learn a little bit about the inside of the planets.
So the planet must be shaken and moving the rings back and forth? That's pretty astounding.
Yeah, it really is unique, and we've learned this while looking at the other planets, at Saturn especially, because it has such extensive rings. But the fact that we have rings at all around the outer planets tells us they're pretty common. But they're also very different from each planet, and that's just, interesting. It tells us that we don't actually know what forms a ring and keeps a ring.
Now, does Uranus have a magnetic field?
It does have a magnetic field, and it's a lot different than what we have here on Earth. So here on Earth, we have a north magnetic pole and a south magnetic pole. For both Uranus and Neptune, actually, that is offset from the center, so it's not directly in the center of the planet. And it's also not just a north and south. It's actually kind of a multipole. So if you could think about 2 magnets crossed with each other, it's almost like that. It's really strange.
So we've really got to go back to these planets and visit them. There's so much for us to learn.
Absolutely.
Well, I'm here with Amy Simon, planetary scientist from NASA Goddard, and we're talking about Uranus and Neptune, our ice giants. What did Voyager 2 discover about Neptune during its flyby that really surprised us?
So Neptune and Uranus are not at all like each other in a lot of ways. Besides being much more Earth-like in its tilt, Neptune's tilted about 28 degrees. It's not the same color as Uranus. So it's a deeper blue. And when we got there, we were shocked to see it had a giant, great dark spot. So it had a big storm that was raging in the atmosphere of Neptune.
A dark spot? You mean sort of like the red spot on Jupiter?
Exactly the same type of thing. It's a gigantic anticyclone, so it's a high-pressure storm, and it was raging throughout the entire flyby. But when we looked again with Hubble, when we could first look at Neptune, it was gone.
You know, on Jupiter and Saturn, we're seeing lightning. And has there ever been lightning found on Uranus and Neptune?
We haven't seen lightning, but that's partly because we expect lightning to form in the water ice clouds. And on these cold planets, the water ice is way down deep. So we're actually seeing methane ice clouds when we see clouds on Neptune, and we haven't seen lightning yet.
Does Neptune have a ring also? And what do we know about it?
So Neptune does have rings as well, but these are not as well formed as what we see on the other planets. They're kind of clumps. So we see arcs, partial rings, at various points around the planet.
You know, in addition to the Voyager discovering the rings, there's also other techniques that we've used to discover and look at the rings of Uranus and Neptune. What's the most important technique?
The best technique we have, especially since we're not up close to them, is to use stars. And when a star passes behind the planet, it gets dimmed out. Well, it turns out when it passes behind the rings, the same thing happens. So we can watch a star twinkling in and out as it goes behind Neptune and its rings.
Any other moons besides Triton that are notable?
Both Neptune and Uranus actually have quite a few satellites around them. In the case of Uranus, they're all fairly small, although we think some of them do have interesting ice on the surface as well. But for Neptune, there's that one big moon Triton, and then the rest are much smaller. So it's more similar to what we see around Saturn.
You know, it'd be fantastic to go back to either one of these and take a look at the moons more carefully. I'd be willing to bet we could find some captured comets, too.
Oh, I think we'd find all sorts of interesting things. We have no idea how many of these moons might be active and actually helping to form that ring system, for example. That's what we found at Saturn with Enceladus. And the fact that we haven't seen the other side of any of these moons, we have no idea what's out there.
You know, we know enough about Uranus and Neptune, just like we knew about Saturn before Cassini got there, because it was only through the Voyager flybys that did that. And so I think we're going to learn an enormous amount when we have an opportunity to go back and really spend some time at Uranus and Neptune. What are some of the mission ideas that we've been talking about?
So we've studied quite a lot of different ways to get out to Uranus and Neptune. I think the biggest problem is they're just so far away, so you can't get out there very fast. So we've looked into, could you do a flyby mission, which is similar to what Voyager 2 did? And if you did that, what would you add? And I think the primary thing we'd add to any mission is an atmospheric probe, because we want to understand what the layers are in the atmosphere, what the temperatures are. But we also looked at orbiters. And these are nice because it gives you a chance to explore that whole system, the rings, the moons, Triton in particular, to see what's going on all sides of those different moons.
When we look at other planets around other stars and we try to figure out what the most populous planet is, it turns out to be about the size of Uranus and Neptune. So this tells us that these are objects we really need to study further. How are we studying them today?
Absolutely. And even to do our own mission to one of these planets, we want to know more before we get there. And so we're using the Hubble Space Telescope. We're actually looking every year now with Hubble at both of these planets. We've also been using the Kepler Astrophysical Telescope to look at the light curves and study how their clouds are changing. Even if we can't see the clouds, we can see the change in their light curves. So we're using as many different ground-based and space-based observatories as we can to look at both Uranus and Neptune.
I'm here with Amy Simon, and we're talking about the ice giants, Uranus and Neptune. What kind of things are we finding out from Hubble and Kepler observations?
So at the moment, we're seeing a lot more clouds on Neptune, and we're finding that they vary on really short timescales, and that's partly because it has winds that blow hundreds of miles an hour, so those clouds change really fast. But we've actually, in the last few years, seen another great dark spot. So we watched one, we discovered it with Hubble, and we've been able to watch it get smaller and eventually disappear. And we think they move around a little bit too, which is interesting. Uranus, on the other hand, has been really, really quiet. So when it passed its equinox, so kind of its springtime, suddenly we saw an outbreak of clouds all over the place, and we haven't seen a whole lot since then. We just see occasional ones. And so they really are quite different planets from each other.
You know, one of the things that we found by Cassini at Saturn was the rings were really shading the planet during certain seasons and causing all kinds of changes in the atmosphere. How long does that take for seasons on Uranus and Neptune?
So a year on Uranus is about 84 years. So each of the seasons is 21 years. And because it's tilted over on its side, that means that, for example, the South Pole wouldn't see sunlight for about 40 years. So it's got really extreme seasons, which help to drive the weather. For Neptune, it takes 164 years to go around the sun, so almost twice as long. But it doesn't have that extreme tilt. And we haven't, at least at this point, been able to observe any seasonal changes because we haven't been observing long enough.
You know, I ask all my guests how they got into this business. What was their gravity assist that propelled them forward and made them the scientists they are today? Amy, what's yours?
So I think I had a two-body gravity assist, actually. The first one being when the shuttle program came around and Sally Ride, I really wanted to be an astronaut, be the first woman on Mars. But honestly, the second one was Voyager 2. And when it flew by Uranus and Neptune and you saw all these exotic worlds and pink ice and all sorts of colors, blue, I was just so enthralled by the planets. I really wanted to be a planetary scientist.
I can resonate with that. Those are just tremendous events that have happened in our space program, and like many others, they have indeed inspired another generation. Amy, you've been working for Goddard now for several years. How did you become an employee for NASA?
My start actually was working on Jupiter on the Galileo mission, and I was doing that as a student and got invited to do a postdoctoral position working on Galileo, at which point I got asked if I would like to help out with Cassini, which was on its way to Saturn. And the instrument I was working at was based at NASA Goddard, and so eventually I moved down to NASA Goddard.
As a civil servant, you provide opportunities during the summer for students to come and work. How many students have been involved in your organization?
Oh, absolutely. It depends on the summer, but some summers we have hundreds and hundreds of students at the center doing all sorts of projects from engineering to science and through all of the different science fields that we have.
You know, for any student that would like to work during the summer, it's www.nasa.gov and do a search on summer employment. Join us next time as we continue our virtual tour of the solar system. I'm Jim Green, and this is your Gravity Assist.